Many, many years ago, back when I was living in Baltimore, I had a good friend called Edgar Allan Poe. And my friend Edgar wrote a short story called The Pit and the Pendulum. And in tribute to him, I'm going to call this little discussion, instead of calling the pit and the pendulum, I'm going to get rid of the T and call it the pi and the pendulum. Because we're going to talk about the relationship between the famous number pi and a swinging simple pendulum. A simple pendulum, we're going to think of it as one with got a string and you got a weight on the end. And the string has negligible weight, and we're going to pull it back a few degrees and let the pendulum go and figure how long it takes it to go from here to there and back. So it's going to swing back and forth. That's going to be called the period, T. T is the period. And we're going to measure it in seconds. Now, you can actually do this in the lab. In fact, we're going to do a little experiment a little later to show this. That if you vary the length of the pendulum, the period changes. So the period does depend on the length. On the other hand, if you vary the mass of the ball at the bottom, it doesn't appear to make any difference what the mass is. If it's a kilogram or half a kilogram or 10 kilograms, the period's still going to be about the same. The period also doesn't seem to be affected very much by how far back you pull the ball. It actually has an effect, but as long as you go stick with a few degrees, it's going to be a negligible effect. So we're going to assume a couple of things. One, we're going to assume that the period does not depend upon the mass of the ball. And we're going to assume that for a given length, the period is going to be constant in the same environment. We'll talk about what that means shortly. And so the period is going to depend upon the length, and the length is going to be L. And we're going to measure the length in meters. So let's just make a wild guess. Let's guess that the period equals some constant times the length. Well, that's probably not going to work out too well, assuming that the constant is unitless. Because if the length is meters, then my units here would be meters and my units here would be seconds, and seconds don't equal meters. So maybe there's something else involved. And it does kind of make sense that there would be something else involved. Because just think about it, if you put a pendulum on the earth, started moving, you really wouldn't expect it to have the same period as if you put it, say, on the moon, because the pendulum's motion is caused by the gravitational effect, and the gravitational effect is less on the moon than it is on the earth. So we'd expect some sort of difference in the period, either greater or less on the moon. We'd have to think about that to see which we would guess it would be. And the constant normally associated with that is g, which is meters per second squared, which is the acceleration due to gravity on a particular place. Acceleration due to gravity. And g, we'll say, is going to vary depending on whether you're on the Earth or Moon or Mars or whatever. So let's just make another wild guess. Let's assume that the period equals a constant times L times g. Well, L is meters, g is meters per second squared. So our units would be meters squared per second squared. And of course that's ridiculous because the time is seconds, and meters squared per second squared definitely is not seconds. So we got something wrong there. We need that seconds, instead of being in the denominator, to be in the numerator. And the way you do that is move the g down below, because now we're going to have length in meters, g in meters per second squared, and we invert and multiply our units, and we get meters times seconds squared over meters, and we get our time is in seconds squared. And the meters have canceled out, and that's a good thing. But the bad thing is the time is seconds squared. We want the time in seconds. Well, one way we can do that is just take the square root of our units. Take the square root of L over G, and so now we have the square root of seconds squared. And of course the square root of seconds squared is going to be seconds. So we can speculate that the period is some constant times the square root of L over G. And now, armed with that speculation, we can actually go and do an experiment. And I would suggest doing this in a classroom. You could give pairs of students different pendulum lengths to try, from say 10 centimeters or a tenth of a meter to a meter or a meter and a half, and then you could collect data of length and the period associated with each length, and from that you might be able to figure out the value of k. So we're going to go ahead and do that, but I'm not going to actually put a pendulum and show myself doing the experiment. Instead, I'm going to just do a computer simulation of the pendulum. So here we go. Let's take a look at that. Okay, so here's my swinging pendulum. It's simulated to be 2 meters long. You see up here the length is 2. And I have a timer up here, and I can use this timer, or I could use a stopwatch, or even a second hand on a clock on the wall to figure out the period. The way I would do that, probably, instead of trying to get the time it takes to go for one swing, I would take the time for 10 swings and then divide it by 10. And that way I could get pretty good accuracy for the period. So you can have students actually make pendula with just any sort of weight and a piece of string, measure their length, measure to the center of gravity of the weight approximately, and just let it swing back and forth a few times, making sure not to make the angle too big, which could have a slight effect on the pendulum and on the period. And you could do this for 2 meters, 1.5 meters, 1 meter, a whole bunch of different lengths, and then you could make a table, and in that table you could have the period versus the length, or the length versus the period, depending on which one you want to have the independent and which one you want to have the dependent variable. Well, in our case, the independent variable is going to be L, because we're trying to find a formula for T, the period. So we control the independent variable L, and then we use a bunch of different lengths, and we figure out how long it takes to do 10 swings back and forth. Divide that by 10. That gives us the period for various lengths. Okay, and I've got the data over here on the right for various lengths. In column A, we have the length in meters going from 0.2 to 0.95 meters. And here we have the period, and you can see as the length gets larger, the period gets larger. About a little less than 1 second for 2/10 of a meter to 0.95 meters. We're up to a period of about 2 seconds. And you will remember we speculated that T, the period, was going to equal K times the square root of the length over the gravitational constant. And our gravitational constant here on Earth is about 9.8 meters per second squared. So I've got that built into this. So that's going to be a constant for this particular planet. And what I want to do is vary the value of K and graph that equation. And my goal is to see if my equation is correct, and I should be able to find a value of K that matches, in which my graph will match the data. And that looks pretty good. And it looks like K is about 6.3. Let's go with that. K is right about 6.3. So going on back to the work that we had done earlier, we now get T equals about 6.3 times the square root of L over G. And remember, our pendulum swings back and forth, and therefore it follows the arc of a circle, which means we would expect circular stuff to come into this in some way. And the circular constant, of course, we're very familiar with is pi. And you may remember that pi is about 3.14159. And so I look at this 6.3 and I say, I wonder if that has anything to do with pi. Well, it's a pretty easy thing to see, I hope, that if you double pi, you get about 6.28, which is pretty darn close to 6.3. 6.3. And of course our 6.3 was just an approximation because we were doing a curve fitting based on our data. And our data is not going to be more accurate than 3 significant figures anyway. So I might have been able to get 6.2 out of this, but 6.3 isn't bad. So I now speculate that t is 2 pi times the square root of L over G. And really, another way to look at this is I've actually kind of found the value of pi. Because if I know that this is 2 pi, and I know the time, the period, then I can back out the value of pi. So we can think of this experiment as in two ways. One, you can think of it as a way of deriving the equation for the period of a pendulum, or the approximate equation for the period of a pendulum, by using what's known as dimensional analysis. We made the units come out correct, and then we looked for pi because we knew it had to be somewhere in here. Or another way of looking at it is, if you started with this formula from physics and assume that this formula was correct, and you wanted to find the value of pi, well, pi is going to equal t over 2 times the square root of L over G. So basically what I've done, another way of looking at it is that that if I knew the period of the pendulum, I knew L and I knew G, I could actually back out a value for pi, an approximate value for pi. And if I use different lengths, therefore getting different periods, I could get a whole bunch of different values of pi and average them to get a pretty good estimate of it. So I think that's a really neat way of showing a number of things, how dimensional analysis can help you back out a formula, how pi has to be involved in this because there is a circular motion involved, and I just think it's a really, really pretty experiment to do, and I hope you enjoyed that. Happy Pi Day.